Hi everybody. Today I'm going to talk to you guys about the speed of light. Now the speed of light is actually one of those topics that is directly from physics but has a kind of a public fascination for a lot of people. Um, in science fiction movies you oftentimes hear about spaceships going at the speed of light or above the speed of light or almost at the speed of light, and weird things happen when you do that. Well, here I'm going to tell you a little bit about the speed of light today, and we'll get into what would happen if you would try to go at the speed of light a little bit later in the course. But for right now, we're just going to talk about what the speed of light is, and then how we might use it to be able to determine some interesting observations about the universe. Well, the first thing you have to know is that the speed of light is, um, in a vacuum, is a constant. And that constant is usually signified with a c. And that C comes from the Latin word for quickness, right? Celeritas. And so C is the speed of light. So you know that from E equals mc squared. C, in that case, squared, actually, is the conversion factor between mass and energy. So C is equal to 3.00 times 10 to the 8th meters per second. So it's about 300 million meters per second. It's just actually a little bit under that. It ends up being, I think, 299 million meters per second instead of 300. But that's okay. We're gonna approximate it to those three sig figs, and it's nice that it's easy to remember that number. So c equals 3 times 10 to the 8th meters per second. It's a speed, right? So it's important to remember that any formula that we use the speed in, we can still use the speed of light in, as long as we're making some approximations about the way light works. You're going to find out later on that light doesn't work the way that we think it does, and so when we talk about relativity, you're going to see that some weird things happen, and those rules that we learned earlier in the year about speed don't really apply the same way. But for now, we can go ahead and say that light speed is just a speed, and it makes sense to use it as a speed. Now, the two main formulas that we're going to use with it are the fact that since it's a speed, we can use that in this formula, v equals d divided by t, which was the very first formula we learned in this physics class. This v here is the speed, d is the distance, and t is the time. But since this is also a speed, we can go ahead and sub that in, and we would end up with the speed of light is equal to a distance divided by a time. In this case, it would be the distance traveled by light divided by the time that it took for the light to travel. Again, this is kind of an approximation, and so we have to be careful about how we use this because we're going to find out when we talk about relativity that weird things are happening when you try to move at the speed of light. Okay, the other formula is actually the wave speed formula, which we learned in Unit 8, which is v equals f times lambda, like that. The speed of a wave, v, is equal to the frequency of that wave multiplied by the wave's length. Now, since light is a wave, we can go ahead and plug in c for the v right there, like so, and find out that c equals f times lambda right there, and that works as well. So now we have our two formulas to be able to manipulate some very basic wave speed and light speed problems. So we're going to go ahead and take a look at one of them right now. So let's say that we've got a probe that we have on the surface of Mars, and we're sitting on Earth trying to control that. So I tried to draw a radio antenna here on the surface of the Earth, which we're using to broadcast our signal all the way over to Mars. And this little purple guy right there is our probe that we're trying to control. Now, the average distance to Mars from the Earth is approximately 225 billion meters. This is a lot. It's a big distance. Now you might think you're used to light traveling almost instantaneously fast from one place to another, but when we're talking about these kinds of distances, we're talking about that's a pretty big distance. How much time would it take for the signal that you send from the radio antenna on Earth to get to your probe on Mars? That's the question. Well, it turns out this is a pretty easy question to answer if we use this formula right here, which is the first formula that we learned in the class, just subbed in for the speed of light. So here we go with that. So the question is, what's the time that it takes for the signal to get there? Well, we know that c equals d divided by t, which we can solve for t like so. Okay, so from that, we know that we're trying to find the time. We know what the distance is. So this is 3, 6, 9, 10, 11. So the time is equal to the distance, which is 2.25 times 10 to the 11th meters, divided by the speed of light, which, as you remember, is 3 times 10 to the 8th meters per second. Oops. Okay, kind of botched that up. Sorry about that. Perfect. So what's 2.25 times 10 to the 11th divided by 3.00 times 10 to the 8th? Okay, so here we go. 2.25 E11 divided by 3 E8 gives us 750. So T is equal to 750 seconds. Well, it's hard to imagine what 750 seconds is because we don't typically use seconds over 60. So I'm going to go ahead and divide by 60 just to find out how many minutes that is. And it ends up being 12.5 minutes. So it turns out that 12.5 minutes is actually a little bit on the low side for the actual number. It turns out that the signal time to Mars should be about 13 minutes, but we're close enough. We're in the ballpark. You can imagine if you were trying to use that signal that you were sending from Earth to drive something on Mars, it might be pretty tricky because you wouldn't know if you had hit something or were close to hitting something for 12.5 minutes. So the rover could keep driving and driving and driving towards the obstacle without knowing that it was going to be in trouble, and you wouldn't know if anything had happened until about 12.5 minutes later. So that's why they don't travel very fast, and it's also why they have some autonomous control. In other words, they're able to stop themselves rather than just blunder into some big rocks. The wave speed formula can also be used to try to figure out the relationship between the frequency and the wavelength. For example, in this case, let's say I'm driving around in my Jeep, as you can see right here, and I'm listening to the Brewer Game on AM 620. AM 620, what that means is that is the frequency at which they broadcast, and that frequency is 620 kilohertz. Now, we don't typically leave things in kilohertz or megahertz or gigahertz for that matter. So we need to convert that back into just hertz. So we're going to multiply that by 1,000. So it ends up being 620,000 hertz is the frequency. So how long are the waves for this particular broadcast? What would a wavelength be? Well, you may know that the wave lengths for AM radio are pretty long. If you've ever driven under a bridge and sometimes lost signal, it's because the bridge is interfering with it because they're of a similar size. So that can be kind of a problem. So let's take a look at it here. The frequency is 620,000 hertz. We know that the speed of light is 3 times 10 to the 8th meters per second. And we know that there's a relationship that looks like this that relates the two together. So I'm going to take that relationship and I'm going to solve it for lambda, which is the wavelength. Looks like a cute little giraffe, right? Is equal to the speed of light divided by the frequency. So now I can go ahead and put in the speed of light, which, as you know, is 3 times 10 to the 8th meters per second. And I can divide that by the frequency, which in this case is 620,000 hertz. Hertz is another way of saying 1 over seconds, and so those seconds are going to cancel each other out. in this case, and we're going to be left just with meters, which makes sense for wavelength. So I'm going to go ahead and get out the old trusty calculator again. We're going to see how this works. So I'm going to take 3e8 and divide it by 6.2 e, let's see, that's 5, right? 5, there we go. And I end up with 483.87 meters. And so I'm going to go ahead and put that right here. 400, I've got 3 sig figs. Let's assume that's a significant figure right there. So 3 sig figs gives me 484 meters. And so from that I can figure out how long the wavelengths are. So obviously 484 meters is a pretty long wavelength. Okay, one final note about these kinds of problems. You don't want to mix the two up. So you can see the area of confusion is probably going to be the fact that you have something with meters here and something with meters there. So you want to be very careful. Obviously this is a wavelength, so we're talking about the distance from one crest to the next. And this one is talking about the overall distance between two objects. So you really don't want to mix those two up. Sometimes people mix up frequency and time, but it's less likely. So more likely is that you might mix up the wavelength and the distance. But remember, distance is how far something is away, and the wavelength is the distance between two successive crests. So again, hopefully this example shows you what I'm talking about there using the distance, and this one shows you what I'm talking about using the wavelength.